Good afternoon, everyone. Thank you for joining us for this second Jean Nicod lecture. As you probably all know, there will be overall 4 lectures. The third lecture will be on Wednesday and the fourth one on Friday, all at 2 p.m. The next one will be, I think, on 45 rue du... Here as well. So all of them will be here. No. On Wednesday here in Salle Jean-Jaurès, and the last one we will be back to Salle du where the first conference was held. On Friday you had the pleasure of seeing John Tooby, and today we have the no less a pleasure of hearing Leda Cosmides for a talk on Adaptationism and Rationality. Over to you.
Thank you. Thank you, Olivier. Can you hear me? Is this okay with you too? Okay. Okay, so as many of you know, human cognition, how the mind works, can be and has been illuminated by comparing human cognition to standards of good design that are specified by a normative theory. But the question is, which normative standards count as good design for an evolved organism? If the goal is to discover sophisticated computational systems in the human mind, which normative standards should guide research? And what counts as a rational inference? So research on the psychology of reasoning and decision-making began in the 1970s by comparing human performance to standards of rationality that were favored by mathematicians, scientists, economists, and philosophers. And the assumption was that good design is equivalent to performance that conforms to these principles of rationality. And then the question became, are humans rational? So the research strategy was to compare, these are examples, to compare deductive and inductive reasoning to first-order logic, Bayes' theorem, various principles of probability and statistics. Questions like, do we learn about the world by generating hypotheses and testing them? And do we apply Karl Popper's standards of looking for violations, not confirmation? You can compare decision-making to Neyman-Pearson decision theory, signal detection theory, expected utility theory, rational choice theory. You can compare moral judgment to normative principles from ethics. Usually people ask, do people consistently apply a single overarching normative principle? And then what counts as an error in reasoning in this way of looking at things? In this research tradition, reasoning errors were defined as having occurred whenever human judgment departs from what these particular normative theories of rationality dictate. So as Kahneman and Tversky very famously put it, the presence of an error in judgment is demonstrated by comparing people's responses either with an established fact, for example, that the two lines are equal in length, in perceptual illusions like the Müller-Lyer illusion, or with an accepted rule of arithmetic, logic, or statistics. So when cognitive performance was assessed by these normative standards, the rationality of human reasoning, judgment, and decision-making was found wanting. There were systematic errors in deductive and reasoning and hypothesis testing, violations of probability theory, preference reversals that violate the axiom of transitivity in rational choice theory. There seemed to be excess altruism. People's behavior did not seem to be explained by the axioms of rational choice plus homo economicus type preferences. And an inconsistent use of moral principles where it looked like people flip-flopped between deontic and utilitarian judgments. So why these deviations from rationality? The most common explanation was that human cognition is just riddled with heuristics, biases, and emotions that produce errors and fallacies, and that these preempt, interfere with, or bias deliberative reasoning. And deliberative reasoning was thought to be necessary for rational judgments, for example, to apply the rules of logic or perform calculations. So this leads to what John and I think of as the paradox of human reasoning. Psychologists focus on normative theories of rational inference that are used in science, mathematics, economics, philosophy, and the research it inspired, and the theories used to explain those results create a paradox. Human cognition is supposedly irrational, riddled with error-prone biases, heuristics, and emotions that cause performance to deviate from the normative ideals of rationality used in science, mathematics, economics, philosophy. Yet, evolved inference systems, both in humans and in other animals, solve natural tasks far better than the most sophisticated existing artificial intelligence systems. Just think about cases like vision, inducing the grammar of a language. Inference is about physical causality that infants make, inferring the beliefs, desires, and intentions of other people, as in the theory of mind literature, with babies 15 months old, or if you're very conservative, 3 to 4-year-olds. How is this possible? Even more puzzling is it's trivial to equip artificial intelligence systems with algorithms that implement statistical decision theories, inferences of first-order logic, and other formal methods of rational inference. And they can search vast problem spaces in seconds, perform lightning calculations, analyze massive databases, and remember a lot more than I can ever remember. So if these methods of rational inference are truly important and key for acquiring knowledge and producing behavior responses that are intelligent and flexible, flexibly responsive to information from the environment, and our mind lacks them, why do evolved organisms perform better on virtually every natural inferential problem that's been carefully investigated? So what's the resolution to this paradox? From the perspective of evolutionary biology, the problem is not that our thinking is irrational. The problem is how psychologists have been defining rationality and how they've been testing for its presence. So let's back up and ask a more fundamental question. Why identify rationality with adherence to these normative theories from logic, mathematics, economics, philosophy? What normative theory justifies the choice of these particular normative theories? Is there a more general view of rationality for which these particular normative theories are special cases? I'm going to argue yes, that a common view of rationality in both in everyday life and in specialized fields, including engineering, economics, evolutionary biology, vision science, evolutionary psychology, is that a choice, process, or behavior is considered rational when it's well designed for achieving a goal, and irrational when it's poorly designed for that function. And on this functional view, there is no goal-independent definition of what counts as rational. So the following, are they rational or irrational? What if you saw me eating charcoal instead of fruit? It would be irrational if my goal was to sate hunger, if I was hungry, but rational if I had injected a poison. Zigzagging from location A to B instead of following a straight line path. It's irrational for saving time and energy. It's rational if you're evading a predator. Your movement needs to be unpredictable. Conversing out loud while you're alone. Irrational for communicating with another person. Rational if you're rehearsing a role for a play. So then, are these methods of inference that have been used, logic, probability, etc., rational? On the functional view of rationality, it depends on what they're for. These specialized and historically recent tools are well designed for achieving very specific goals that are evolutionarily recent, like producing scientific knowledge, understanding markets, and guiding behavior in mass societies. From the 1400s to the present, there's been massive technological change with increasing literacy, more reliable data storage technologies like books, decreasing costs of communication and travel that changed the world beyond anything known by our hunter-gatherer ancestors. Theories, hypotheses, and data became more widely shared, debated, vetted, and stored, allowing the cultural accumulation of knowledge in ever larger populations. Markets arose in which millions of anonymous individuals cooperate in complex networks, and people from distant locations with different moral norms were brought into contact with each other. So in these new conditions, the normative theories of rationality that have been traditionally used in psychology may be well designed for those functions, producing scientific knowledge, understanding market dynamics, maybe fostering cooperation in mass societies with global contact. But what privileges methods develop for these modern goals as the metric against which human rationality is measured? I would say nothing. Rationality in an evolutionary perspective looks different. Achieving these modern goals played no role, no causal role, in selecting for the design of the mind. They are not the problems the mind should be well designed for solving, at least not as they have been presented to people. To discover rational design in the mind, we need to take a functional view of rationality, an evolutionary functional view. And that's what the Adaptationist Research Program does. So the overall title of our series is the Adaptationist Revolution is Transforming the Cognitive Sciences. Maybe that's, well, gone a little bit far, but could go farther. And so I want to explain what this is. It provides a meta-normative theory of rationality, a theory of what should be considered rational, that's appropriate for evolved organisms, including their cognitive systems. And in this view, an evolved computational system has a rational design if its features are well tailored for solving an adaptive problem that was faced by the hunter-gatherer ancestors from whom we are descended. So to recap a couple points from John's talk on Friday, organisms are composed of many machines, that is, systems that are improbably well organized to solve problems related to reproduction, like hemoglobin being improbably well designed for delivering oxygen to tissues, et cetera, et cetera. Chance alone does not produce organic machines that are improbably well designed for solving problems. Natural selection does. Organic machines that were designed by natural selection are called adaptations. And they exist, adaptations exist, because they solved problems that contributed to an organism's ability to produce offspring in past environments. They were produced by a particular causal process. Some organic machines evolved because they perform computations that regulate physiology and behavior. And these are computational adaptations. And like adaptations, they exist because they solved problems that contributed to an organism's ability to produce offspring in past environments. For example, detecting and evading predators, learning what's edible, managing foraging risk by sharing food with others. An adaptation's function, in evolutionary biology, an adaptation's function refers to the adaptive problem that's selected for its design. An adaptation can solve other problems by virtue of its causal properties, just like I can use my phone as a paperweight, but it wasn't designed to be a paperweight, but it can be used for that. But these beneficial effects are not its evolutionary function. Producing those effects plays no role in a causal explanation for its design features. And given enough time, natural selection produces adaptations that are well designed for solving ancestral adaptive problems. That is, their design is rational in the sense it's well designed for achieving a goal. Therefore, computational adaptations that produce inferences, judgments, and choices should be well designed for solving the ancestral adaptive problems that selected for their design. And analyzing these problems is the key to recognizing and discovering sophisticated computational systems in the mind and sheds new light on human reasoning and decision-making. An adaptation analysis is a 5-step program for discovering the design in the mind. It's not for just like looking at things and say, what was it for, but for discovering new things. Step 1, identify an enduring adaptive problem that our hunter-gatherer ancestors were likely to have faced. Ask yourself, like David Marr in his levels of explanation, what is the goal of processing? Things like cooperating for mutual benefit, detecting changes in the state or location of animals. Step 2, do a careful task analysis of that adaptive problem, what David Marr would have called a theory of the computation. To solve this adaptive problem, that is to achieve the goal of processing, what design features would a computational system need to solve that adaptive problem well? And what information would have been available in ancestral environments for solving it? This is equally important. And many fields of research can be helpful for this. Evolutionary game theory, agent-based models, behavioral ecology, including studies of existing hunter-gatherers, non-human primates, et cetera, and studies of ancestral environments where you have information not just from paleoanthropology and paleoarchaeology, but from physics, geology, botany, zoology, and so on. Step 3, use that task analysis to derive hypotheses about cognition, because a computational adaptation should deploy algorithms and representations that are well engineered for solving the problem that's selected for its design. So you ask, what properties might a system that evolved for this function have? Step 4 is test your hypotheses empirically. This is an empirical research program. And use whatever methods are appropriate. It might be laboratory methods from all the branches of psychology or from behavioral economics. It might be cross-cultural field tests. There might be dissociations that are caused by brain damage or developmental disorders, evidence from social and cultural anthropology. And that includes testing against alternative computational designs that have been proposed. And step 5 is simply evaluating the empirical evidence, because the question you want to know is there evidence for a computational system that's well designed for solving this adaptive problem? Adaptations are recognized by evidence of special design, that they are well designed for solving an adaptive problem. Is the goal of processing achieved? If so, are the cognitive processes responsible for achieving that goal specialized for that function, or are they more general? Do they seem better designed for an alternative adaptive function that you didn't consider or that could produce the same performance? So adaptationist analyses like this provide principled, non-arbitrary criteria for judging rationality. A careful analysis of an adaptive problem serves as a normative theory of good design. Theories of adaptive functions specify the goal of processing and what we count as a good method for achieving it. The study of reasoning and choice looks very different when considered from this perspective. Many fallacies disappear and well-designed reasoning appears when cognitive performance is evaluated against theories of adaptive function, which are normative theories of good design. So using several case studies, I had initially hoped it would be 6, and then I realized I was insane and could never do all 6. I'm going to try to illustrate principles of adaptive design and show how research using each principle led to new discoveries and insights, and how research ignoring it led to faulty conclusions. So case study number 1, the principle is that to discover a well-designed reasoning mechanism, you need to present stimuli in an ecologically valid format. And the example I'm going to use is Bayesian inference with natural frequencies. So first, let me back up and talk about a design principle. Computational adaptation should be ecologically rational. That is, designed to operate well in the ancestral environments that's selected for their design. Now consider this incredibly ordinary but computationally spectacular experience. Looking at, oh, you can't see this. Right here, the grass looks green at sunset and at noon. Color constancy is maintained over the day, despite vast changes in the spectrum of light that's reflected off the grass. Because color vision evolved for daily variations in solar illumination from our sun on our Earth. And grass reflects more short and medium wavelengths at noon and more long wavelengths at sunset. But the grass doesn't look red at sunset because our visual system subtracts out the fact that the whole world is bathed in red. Our color constancy mechanisms are ecologically rational. They're designed to operate well in the ancestral environments as selected for their design. That's their proper domain, to use Dan Sperber's term. He also distinguishes that from the actual domain of a mechanism, which is all of the conditions that meet the input conditions of the mechanism. So, for example, under regular light bulbs inside, you maintain color constancy pretty well. The spectrum's close enough. So if color constancy mechanisms are so well designed, why do these two cars look the same? One's red and the other's black, if you were looking at them at noon. This is a failure of color constancy that happens under sodium vapor lights in a parking lot. Sodium vapor lights cast a literally unearthly spectrum. This is the spectrum that you get from those lights, and this is during the day, what you get from the sun. But does that failure in color constancy, under those lights mean that color vision is flawed, error-prone, biased? No. There is no such thing as a mechanism that can operate well in all possible universes. Color vision evolved on Earth and maintains color constancy well across typical variations produced by our sun, but not under alien light sources. Now let's say that aliens have abducted humans for study, and they're studying our color vision. And they do all of their experiments under sodium vapor lamps because they don't know better. They don't know what changes in terrestrial illumination were like on Earth. They don't know the spectrum that humans were exposed to during their evolution. They would never discover that we have a sophisticated computational system for maintaining color constancy on Earth. They might conclude that human color vision is irrational, poorly designed. They might even speculate that humans did not need good colored vision during their evolution. This is obvious, right? Yet the best known studies of judgment under uncertainty, about inferences about probability, use stimuli that are the conceptual equivalent of sodium vapor lamps, and concluded the human mind lacks mechanisms for reasoning soundly about probability. So the case one is going to be Bayesian inference. I'm going to show you how to elicit errors and how to elicit correct answers from the same statistically naive subjects. So a normative theory that's from evolutionary biology. In behavioral ecology, they develop lots of normative theories, including models of what would count as optimal foraging for various species. They do task analyses of adaptive problems. Because efficient foraging requires animals to make judgments under uncertainty, optimal foraging models do incorporate elements of probability theory. And a typical finding is that insects, birds, and other animals behave like good Bayesians when they make foraging decisions. So you've got bird brains and insect minds versus a human mind. Right? A still dominant view in psychology, despite this, is that the human mind is too limited in capacity to do what bird brains and insect minds do. Is this the same quote as before? In making predictions and judgments under uncertainty, this is Kahneman and Tversky again, people do not appear to follow the calculus of chance or the statistical theory of prediction. Instead, they rely on a limited number of heuristics, which sometimes lead to reasonable judgments and sometimes lead to severe and systematic errors. And that was based on, you can replicate any of their experiments, they're very replicable, most of them, demonstrating the conjunction fallacy, neglect of base rates, answers that deviate wildly from the calculus of Bayes' theorem. So why the difference? Non-human animals were tested using foraging situations, ecologically valid situations as stimuli. So for example, food would be stimuli. The animals discover the frequencies in different patches where they can forage. But humans were not. The stimuli presented to humans in the problems given were in a format that arose recently from large-scale data collection and random sampling. Probability data was provided and requested in a format that did not exist ancestrally. Normalized frequencies randomly sampled, applied to single events. Not what I'm going to explain, not natural frequencies, which I'll explain in a minute, which elicit dramatically different differences in performance. This is just to give you a sense, and I'll explain in a second, of the difference between testing the same problem under sodium vapor lamps, the normalized frequencies, probabilities of single events, versus frequencies. This is data on the medical diagnosis problem that was given by Cassels et al. In 1978 to, and this should frighten you, to faculty and fourth-year clinical medical students at Harvard Medical School, okay? The problem is this. If a test to detect a disease whose prevalence is 1 in 1,000 has a false positive rate of 5%, what's the chance that a person found to have a positive result actually has a disease, assuming that you know nothing about the person's symptoms or signs? You would hope that your doctor could tell you the answer to this. This is the performance at Harvard Medical School. Only 18% gave the correct answer of 2%. In fact, most said 95%. They weren't like a little bit wrong. They were wildly wrong. The other The other bars are all Stanford undergraduates that John and I tested. You could say maybe people don't know what a false, you could see that they do the same as the MDs. When you given exactly the same problem, you could say maybe they don't understand what a false positive rate is. So you can clarify that in plain English. You can say, and you raise performance a little bit, but to like 36%. But when you give the problem in a more ecologically valid format, which I'll describe in a second, you get very, very good performance. That looks nothing like the sodium vapor lamps. And by the way, the people who responded correctly under the sodium vapor lamps with the single events and normalized frequencies, they had translated the problem. You could see on their paper that they had translated the problem into frequencies. Okay, so let's dissect the difference. I'm going to do it using a more foraging-related problem. So this is how you elicit poor performance. Imagine you want some ripe red apples from an orchard. There's a 20% chance that a tree in this orchard is an apple tree. If it is, there's a 75% chance that its apples are not red. But some of the other trees also have red fruit. 37.5% of them do. You can see a tree with red fruit in the distance. What is the chance that this tree with red fruit is an apple tree? It's a conditional probability problem. This is the base rate, the prior probability of the hypothesis, that is, that something's an apple tree. This is the true positive rate. If it's an apple tree, how likely are you going to get the data of red fruit? This is the false positive rate. If it's not an apple tree, what's the probability of red fruit? This is the posterior probability, the probability of the hypothesis given the data being red fruit, the hypothesis apple tree. And notice that it's asking for the probability of a single event. So when problems are presented in this format, few people answer correctly. Base rate neglect is common. That is, answers do not seem to reflect the low prior probability of apple trees in the orchard. And if you think about it for a second, normalized frequencies are problematic because each is derived from a random sample of different subsets of the population of trees in the orchard, making it difficult to recombine all of those different rates, the true positive rate, false positive rate, et cetera. So this is a representation of that problem. You've got the probability, you can see you've got a tree, we're considering a tree in the orchard, the probability it's an apple tree is 0.2. Then there's conditionalization of the other data. So this 75% is 75% of this population, right? Not of the whole population, but of this population. It's conditionalized on this. This false positive rate conditionalized on this. Right? So each percent is normalized on a different population. And so also there's no information about base rates at this bottom level where you're seeing the trees. Right? So the base rates normalized on this whole population, the 20 trees. Those are the apple trees. The true positive rates normalized only on apple trees. The false positive rate normalized only on trees other than apple trees. And then you can ask, what's the chance of a single event? I always found this a very puzzling concept. A 20% chance that a tree is an apple tree. It's either an apple tree or it's not an apple tree. Or that when they say on the weather, there's a 40% chance of rain today. Today it's either going to rain or it's not going to rain. Single events either happen or they don't. The probability of a single event cannot be observed. It's usually people think of it as expressing a frequency, like on days with barometric pressure measurements like this, there's a 40% chance of rain. Or it can reflect a subjective degree of confidence, but you can ask based on what? On the frequencies, on something else? And it's hard to combine the working parts that you need to put all that information together because you need formulas, decimals, multiplication, division. So with each normalized on a different population, you need a formula to combine the parts, and that's Bayes' rule, which is this mess. And people are bad at doing that. Now, how to elicit good performance? First, consider the adaptive problem, your task analysis. Did our hunter-gatherer ancestors need to make judgments under uncertainty and update them as conditions change? Yeah, it's necessary for foraging and many other decisions. And updating those frequencies is needed because the success rate, for example, in a given foraging area changes over time with how many others are exploiting it, the season, and so on. So you might have as just a simple first-order hypothesis, maybe I should expect the evolution of mechanisms that were good at acquiring probability information and updating it under ancestral conditions. Was ancestral data available for solving a problem like that? Yes. The absolute frequencies of objects and events in the world. Encoding mechanisms might use representations with a compatible format. Representations of absolute frequencies are easy to update if they're stored. So another hypothesis, you might expect mechanisms designed to acquire these frequencies. And indeed, there is evidence of automatic frequency encoding as a feature of incidental learning. And it's known that many animals acquire frequencies, especially number over unit time, and update them. So Randy Gallistel just says you can reanalyze classical conditioning as non-stationary multivariate time series analysis being conducted very well by animals. Then you can ask, well, what sampling method would our ancestors have had to sample data about frequencies? Natural sampling is recording events as you encounter them in the world. And that's rarely a random sample from a population, which is needed for normalized frequencies. So you might have the hypothesis that the design of procedures that operate on frequency representations should assume a random sampling method. The procedures themselves should be designed to assume that method. So ancestral format and sampling method, natural frequencies were available to our ancestors. The absolute frequency of events as you encounter them, that is naturally sampled, not randomly sampled. So let me give you an example of a natural sample. What do you encounter while walking through the orchard? Well, apple tree with green, lemon, cherry, et cetera, et cetera. You're walking through the orchard. Incidentally, your mind is picking up the frequencies of different things in the orchard, categories in the orchard. Now, let's look at the same problem with this kind of format. Imagine you want some ripe red apples from an orchard. The orchard has 20 fruit trees. 4 are apple trees, and 3 of them have red fruit. There are 6 other trees with red fruit. How many trees with red fruit are apple trees? Blank out of blank. How many apple trees with red fruit were there? That's hits. There were 3. How many trees with red fruit? The 3 apple trees and the 6 other trees. That's 9. It's 3 out of 9, or 1 out of 3, or 33%, or however you want to express it. Very, very simple. This is a representation of the same problem in natural frequencies, which are automatically encoded by the mind. You need to know the hits, apple and red, the false alarms, other and red, and it's just hits out of hits plus false alarms. Very straightforward. It's more about sets than it is about anything else. In this ancestral format and sampling method, normalized frequencies are unnecessary, and the low base rate of apple trees in the population is already accounted for because when apple trees are rare, you encounter fewer of them. It's just 4 out of 20. So is the false positive rate accounted for in your natural sample. All the working parts are in the same format from the same population. They're easy to recombine to answer new questions. And Gert Gigerenzer and his colleagues have recently found that with natural frequencies, 9-year-olds do better than Harvard Medical School faculty and 4th-year clinical students. He uses with the small kids icon arrays to represent natural frequencies. These are cookies. Out of every 15 cookies in the cookie jar, 3 are round and made of chocolate. The other 12 are square. Of the 12 square cookies, 5 are also made of chocolate. Imagine a pile of chocolate cookies from the jar. How many of these are round? Blank out of blank. 9-year-olds, they get the correct, numerically correct posterior probability 64% of the time. And 78% of those children, they were given 6 problems, got 50 to 100% of them right. So something was being missed by studying judgment under uncertainty under sodium, the conceptual equivalent of sodium vapor lamps. Okay, case study 2. Judgments that look like normative violations may actually be very well designed for solving a recurrent adaptive problem, but it may be an adaptive problem that you were not considering. And the example I want to give you here is risky decision-making versus prospect theory. So Kahneman and Tversky's prospect, I sound like I'm picking on them. I don't mean to be picking on them. It's just these are easy to explain in a short lecture. The claim of prospect theory, based on experiments I'll show you, is that losses loom larger than gains. And what do they mean by that? The empirical claim is that in choosing between a risky option and a sure option, both of which have the same expected value, people are willing to take a bigger risk to avoid a loss than to achieve an equal size gain. The normative theories it challenges is expected utility theory approximately predicts indifference between options with the same expected value, but people are not indifferent. And rational choice theory expects preferences to be transitive, but what I'll show you are loss and gain frames elicit irrational preference reversals that violate the axiom of transitivity. So let me show you the loss and gain frames. This is one of the most famous problems that they used in science, I think it was, to illustrate this problem. Imagine there's an outbreak of a disease that will kill 600 people if nothing is done. That sounds laughable today, just 600 people. Which of two programs to combat the disease would you favor? This is the loss frame. If program A is adopted, 400 people will die. If program B is adopted, there's a 1/3 probability that nobody will die, and a 2/3 probability that 600 people will die. The expected value of programs A and B, notice that they're the same. 200 lives saved, 400 lives lost. 200 for certain with A, 200 on average with B. Okay? This is the gain frame. If program A is adopted, 200 people will be saved. If program B is adopted, there's a 1/3 probability that 600 people will be saved, and a 2/3 probability that no people will be saved. So this one's in terms of lives saved, the other one was expressed in terms of lives lost, but this one has the same expected value as the other problem. The thing that will happen in the world, the material consequences are the same. So the loss and gain frames express situations that are logically and mathematically identical in terms of their material consequences in the world. 200 live, 400 die, with certainty with program A, on average with program B. Now let's look at the normative theories of rationality. Expected utility theory, a first order prediction of it would be that you'd be indifferent between these two programs because they have the same expected value, 200. But people are not indifferent. So for example, with this loss frame, 80% of people prefer B, the risky option. They prefer the risky option here, right? It could save 600 people. Rational choice theory, it can apply to many different fields, but I'm talking here about its typical application to microeconomics, especially in consumer theory. It predicts making the same choice in the loss and gain frames because it's the same material consequences, and whether you choose A or B, it doesn't matter. Rational choice does not require indifference. And because the options are defined by their material consequences is why you should make the same thing. The same choice in both frames. So rational choice theory would say always choose the available option with the highest utility, given your personal preference order. That preference order is stable. That's a simplifying assumption made in microeconomics. Perhaps it's described by a utility function, which is it's kind of representation. It's a ranking of all conceivable options. And rational choices will respect the axiom of transitivity. That is, if you prefer A to B in one choice set, then when you encounter another choice set, you should also prefer A to B. So if you turn out to prefer B to A in another choice set, that's a preference reversal, and you've violated the axiom of transitivity and made an irrational choice. That's the argument. Okay. The loss frame, 80% prefer the risky choice, but do they also in the gain frame? No. 70% prefer the sure choice. That's a preference reversal, even though the material consequences are the same whether you put it in terms of loss or gain. This violates expected utility theory. It violates rational choice theory. It looks like people are doubly irrational. And the explanation proposed was prospect theory. The idea is you have a stable preference. Loss aversion is a stable preference. So you're willing to take a larger risk to avoid a loss than to achieve an equal size gain because of the shape of a preference curve. And the loss frame activates loss aversion. And supposedly, no normative theory of rationality can explain these choices, supposedly. In the meantime, there was a normative theory from behavioral ecology that explains these results without invoking framing effects and correctly predicts when choices will flip from high to low variance options, from risky to sure options, or even low variance ones. It's a branch of optimal foraging theory called risk sensitivity theory. And a key concept is, what is your need level? So here's a bird. And this bird's decision is, where should I forage today? There's 2 patches, A and B. And each patch has the same expected value, 200 seeds a day. So this is patch A. The bird will have a 100% chance of getting 200 seeds if it forages on patch A. Here's patch B. This is a high variance patch. There's a probability of 1/3 that it'll get 600 seeds, and a probability of 2/3 it'll get nothing. Now the question is, what's its need level? How many seeds does it need to live another day? This is a problem many animals face. Let's say its need level is 200 seeds. It needs 200 seeds to live to tomorrow, right? Well, obviously, the bird should forage on the low variance patch because it's certain to get the 200 seeds it needs to live to tomorrow. Whereas it has a 2/3 chance of dying if it forages on patch B. Let's say it needs 400 seeds a day to live to tomorrow. Then it should clearly forage on patch B because there is no chance that it will get 400 seeds on patch A. It'll die, right? So let's apply this to humans for a second. These people have to decide for the disease problem, how many lives do I really need to save? What is my minimum number of lives that I feel I need to save? You can, as an experimenter, Sandeep Mishra and Larry Fiddick did this. As an experimenter, you can either specify or elicit a minimum need level, or you can have the subject report it after they've already made a choice. And they also tested certainty versus low variance, which doesn't matter. There's nothing special about certainty here. And so do people choose rationally given their need level? Well, the ones that when you specify you need to save a minimum of 200 lives, they choose program A. When you say you need to save 400 lives or 500 lives or 300 lives, then they choose program B. They do the thing that's perfectly rational given the need level. When no need level is specified, which is what was true in the Kahneman and Tversky versions, then framing effects reappear. Oh, I should say, there's no framing effects whatsoever when you specify a need level. None. 0. They go away. They reappear when you specify no need level. But why? It turns out it's because whether you talk about death, then people feel they need to save more lives than when you talk about saving lives. And so you have, they specify no need level, but they asked right after the subject made a choice, what was the minimum number of lives you felt you need to save? And some people thought, I need to save at least 500 lives, 400 lives. And those subjects chose the risky option. And some people said, I need to save 200 lives. It'll be really bad if I don't save at least 200 lives. And they chose the sure option. And the higher the minimum number of lives they felt they needed to save, the more likely they were to have chosen the risky option. It's perfectly rational. Ambiguity aversion is also explained by the same model. The claim that many economists keep making is that people are averse to ambiguity, and for a problem like this, that they avoid ambiguity because they have a preference, again, it's the preferences that are invoked, for known risks over ambiguous options. Risk sensitivity analysis would say, well, ambiguous options, maybe they're usually interpreted as high variance options. This is easy to test because you can dissociate variance and ambiguity. So imagine a lottery. You have to choose one of 2 boxes. They have black and white balls in them, but you don't know what the distribution of balls is in each box. Well, actually, in the known risk box, you know that the probability of drawing a black ball is 0.3 or other probabilities in other conditions. In the ambiguous box, the probability of drawing a black ball is always 0.5 because it's determined by, you're told, the distribution of balls is going to be determined by a random draw from poker chips that are from 0 to 100. Right? So we're going to draw from that. So on average, there'll be 50% on average, but you don't know exactly what it's going to be. And then you vary the need level. How many black balls you need to draw in order to win a lottery. What you're seeing here is the ambiguous box. This is the percent of subjects choosing the ambiguous box. Whoops. And this is the probability of drawing black for the known risk box. And what you're seeing is when black is when their need level is higher than the expected value. White is when their need level is lower than the expected value. And they are preferring the ambiguous box when it has a higher probability of getting them the number of balls that they need. And they actually even continue to prefer it even when the known and ambiguous risk box have the same expected value. They even are indifferent when it's even 0.6 probability of winning in the known risk box. And this is the actual probability of winning versus the decisions people made. And what you're seeing here is the data points are hugging the line really well. So to summarize the risk sensitivity theory, this normative theory from behavioral ecology shows that the need level determines when risky versus sure options or low variance options are chosen, regardless of loss versus gain frames. Those frames become irrelevant. It eliminates framing effects. It predicts when people will avoid versus prefer ambiguous options over known risks, without positing odd preferences such as loss aversion or ambiguity aversion. And it shows that choices that look like they're preference reversals are not. They're rational choices, given what your preference is, what I need to accomplish. Case study 3. I just want you to think about everything that was missed by not thinking about the adaptive problem in that case. Case study 3, choices that deviate from economic rationality, or certain views of economic rationality, may be the most adaptive fitness promoting strategy, not a bias. An example I'm going to use is the evolution of generosity in one-shot interactions. So game theory is a source of normative theories about social behavior. You can have normative theories about social behavior, very highly analyzed ones. Game theory is a tool for analyzing what people call strategic social behavior, which is how agents will behave when they're interacting with other agents who can anticipate and respond to their behavior. Economists use it to analyze how people respond to incentives that are present in the immediate situation. And their models typically assume rational actors who calculate the payoffs of alternative options, anticipating that other players will do likewise, and choose the option most likely to maximize their short-term profits. They make homo economicus preferences. You don't have to be an economist to make homo economicus preferences, but people wanted to test this in experimental economics. Evolutionary game theory is a different source of normative theories. It does not assume ecologically rational, economically rational agents who can reason about the reasoning of other agents via backward induction, if you're familiar with that term. It's used to model interactions among agents that are endowed with well-designed decision rules that produce situationally contingent behavior. These are sometimes called strategies, although there's no conscious deliberation implied or ruled out by that term. You can use it for study the evolution of cooperation in bacteria, fighting in spiders. The results are derived either analytically in the form of theorems or in more complex cases through agent-based simulations of natural selection. So whether the decision rules being analyzed are designed to regulate foraging, fighting, cooperating, whatever they're designed to regulate, the immediate payoffs of those decisions in food or resources are translated into the currency of offspring produced by the decision-making agent, and these offspring inherit their parents' decision rule, and the decision rule or strategy that garners the higher payoffs leaves more copies of itself in the next generation than alternatives that garner lower payoffs, and then you run it many, many times over many generations to see what emerges. So by analyzing the reproductive consequences of alternative decision rules over generations, evolutionary biologists can determine which strategies natural selection for a given domain is likely to favor and which are likely to be selected out. And this source of normative theories can be tapped for any domain in which organisms make consequential choices. And it's been applied extensively to the evolution of cooperation for many years. with clear results. Strategies that indiscriminately provide benefits to others, including those who do not reciprocate, are eventually eliminated from the population because they incur reproductive costs without compensating benefits. They're outcompeted by strategies that cheat, defectors, strategies that accept benefits without reciprocating them. The issue is a failure to reciprocate by design, not by accident, right? Because what's happening in natural selection is it's a selection of alternative designs, okay? So by design, I mean either intentionally in a common sense of the term, or you can think by virtue of the strategy implemented in the organism's head, by virtue of their disposition, by virtue of the calibration of their mechanisms, et cetera. So a cheater or a defector is an agent endowed with decision rules that accept benefits offered by other agents without reciprocating or otherwise satisfying their requirements. Accidents and innocent mistakes do not reveal a cheater. And because even good cooperators are going to sometimes fail to reciprocate. They might be injured. They might have gone foraging and just not found anything that they can then share with you. They might have just forgotten. It might be an oversight. But it would be a fitness error to exclude good cooperators for that reason. Right? Eventually, you'll have nobody to cooperate with, which is really bad if you're a forager. Experience high variance in foraging success. And it's a fitness error because you'll end up missing out on strings of benefit transactions if you exclude good cooperators who may have just made a mistake. And these selection pressures have shaped our psychology. I don't have time for case study 4. The principle I wanted to illustrate that is a cognitive adaptation for reasoning may be specialized for a specific domain and therefore equipped with representations and procedures that are content-rich rather than content-free. Because there are inference and also implicit categorization procedures that are activated by cooperation that are content-rich and distinguish between intentional failures to cooperate and innocent mistakes. So a lot of my research has been on social exchange, two-person cooperation. It activates inferences and information search procedures that cause a detection of violations of agreements to exchange when those would reveal cheaters, but not when they would reveal an innocent mistake, when the potential violator would just have made an innocent mistake. In collective action situations with group cooperation, there's a very interesting unobtrusive measure of implicit categorization, and it shows that not all failures to contribute are the same. Intentional failures to contribute, the person gets tagged as a free rider, whereas a person who fails to contribute because they, by accident or they failed in their foraging attempts, is still tagged as a good cooperator. And in this domain, the categorization mechanism, slice this moral domain very, very thinly. So you can even do experiments where the individuals in the collective action, some of them are free riders in the sense that they've agreed to, they've crashed on a desert island, they've all agreed to forage and give food to the people who were injured. Some of them don't contribute food on given days, so one moral violation. Others of them steal from the group, like they might steal a Swiss Army knife or some other resource from the group. They are distinguished in the minds of subjects when you look at this implicit categorization of the people. They are not put into the same category. It's not just a category of moral violators, different kinds of moral violators. And this measure does not necessarily produce categorization. You can show that conditions where it does not, you can make a distinction and it doesn't produce categorization. So anyway, back to repeated interactions that select for reciprocation. The reason natural selection favors strategies that deliver benefits to others contingent on reciprocation is that they outcompete defectors, strategies that don't deliver benefits, because reciprocators harvest the fruits of mutual cooperation over many repeated interactions. So how do we then explain generosity in one-shot interactions? Benefits given to someone you will never meet again. So no reciprocation is possible. So that raises a puzzle from behavioral economics. Behavioral economists study cooperation in the laboratory by having people interact in games where monetary payoffs for different choices are carefully controlled. Dictator games, ultimatum games, etc. And sorry. And then what they find is that in one-shot anonymous interactions, so you're told this is only going to happen once, and you don't know who this person is, and you'll never know who this person is, and they'll never know who you are. You'll never meet. The Homo economicus models of short-term profit maximizing predict no generosity, no cooperation, no trust, and no punishment. Yet, in many one-shot anonymous games, people give more, cooperate more, trust more, and punish defection more than Homo economicus models predict, even when the experimenter tells them that the interaction is one-shot and anonymous. But why? Generosity in anonymous one-shot games is irrational given the standard theories, including some evolutionary ones. So what explains this? This is called excess altruism. What's explaining the excess altruism? The response has been that because delivering benefits in a one-shot anonymous interactions is considered irrational, some social scientists have viewed it as evidence that the psychology of cooperation was shaped by group selection rather than selection operating on individuals like Sam Bowles, Herb Gintis, etc. But are these behaviors really excess altruism, that is beyond what can be explained by selection on individuals for direct reciprocity? So let's turn to something slightly different than evolutionary game theory. I'm going to call it adaptationist game theory, where you model the information processing problem and you let the psychology evolve in response. Selection doesn't occur in a vacuum. The physical and social ecology of a species shapes the design of its adaptations. And our hunter-gatherer ancestors lived in small interdependent bands, which had many encounters with individuals from neighboring bands. And adaptations for direct reciprocity evolved to regulate cooperation in an ancestral world in which most interactions were repeated. So the high prior probability that any given interaction will be repeated should be reflected in the design of computational adaptations regulating direct reciprocity. So should the fact that you have interacted at least once with a person. Max Krausenau modeled that social ecology and showed that meeting with an individual once is itself a good cue that you'll meet again. So by modeling the information processing problem and letting the psychology evolve in response, you realize that the question whether an interaction is one-shot or repeated is a judgment made under uncertainty. And so you can ask what decision rules does selection favor when this judgment under uncertainty problem is part of the model, which Andy Delton and Max Krausenau took the lead on these models. So the evolution of generosity under uncertainty. In most agent-based simulations of the evolution of cooperation, the behavioral strategies are particulate, indivisible atoms. They don't have internal cognitive components that can evolve. And the simulation environment has either one-shot or repeated interactions, but usually not both. But what happens if these strategies have a cognitive architecture that can evolve, and the social environment includes both one-shot and repeated interactions, as does real life? It turns out that generosity in one-shot interactions evolves easily when you take this under conditions of uncertainty, when you model this problem. So in real life, you never know with certainty that you will interact with a person once and only once until the second before you die. Then you go, oh, I never met Olivier again. 1 minute. Categorizing an interaction as one-shot, or give me 2 minutes and then I'll finish everything. Categorizing an interaction as one-shot or repeated is always a judgment made under uncertainty based on probabilistic cues. Am I far from home? Oh, I'm in Paris, not in Santa Barbara. Did this person marry into my band? So in deciding whether to initiate a cooperative relationship, a contingent cooperator has to use those cues that are available to decide whether to cooperate or defect. And they have to make trade-offs between two different errors. A false positive is what's really a one-shot interaction is mistakenly categorized as a repeated interaction. So I cooperate, but my one-shot partner defects, and I suffer a one-time loss. A miss is a repeated interaction. If I'm going to interact with Olivier many, many times, but I think it's a one-shot interaction. I'm never going to see him. I can do whatever I want. I'm never going to see him again. Right? So I defect, which will trigger from a contingent cooperator defection in return from what could have been a long-term cooperative partner. So the cost is a missed opportunity to harvest the gains in trade from a long string of mutually beneficial interactions, which is a big problem for the point of the evolution of anything. So when you let the adaptations evolve, in a population, we use a population of contingent cooperators, they use tit for tat usually. The cost of a miss is usually much higher than the cost of a false positive. So in these agent-based models, the decisions to cooperate or defect were based on two pieces of information. The base rate of one-shot interactions in the population. This was given as innate knowledge to our agents. And it varied up to 70% of the interactions being one-shot. And a Q summary for each new partner, which is a number. I'll explain in a second. And then we watched how does the cognitive architecture use that information? How does it evolve to use that information? So the Q summary for a new partner, it's just a number. It serves as a hint to whether the agent's interaction with that partner is going to be one-shot or repeated. They're never perfect predictors. They're drawn from one of two normal distributions for one-shot, numbers associated with one-shot versus repeated interactions. And those distributions overlap by different amounts, right? Sometimes quite a lot. And they're used to compute the belief that the interaction will be one-shot or repeated. And you have agents cooperate when they believe an interaction is repeated, otherwise they defect. So in one set of simulations, the motivations to cooperate or defect depended on that belief. And what evolves is a decision threshold determining how strong the Q summary has to be, in order to classify the interaction as one shot, therefore I should defect. And what happened was that selection favored a threshold of evidence that's so high that most interactions were classified as repeated, triggering cooperation, even if they were one shot. So credulous agents evolved because the cost of missed opportunities, the fitness cost, was so great, much greater than the cost of cooperating wrongly in a one-shot interaction. The second simulation set, motivation to cooperate is what evolves. It's a regulatory variable that determines the probability an agent will cooperate given its rational belief that the interaction is one shot. The agents were perfect Bayesians. They are this typical psychologist's dream of a rational agent. And they formed rational beliefs about whether this is a one-shot or repeated interaction by using Bayes' rule to integrate cues that the given interaction is one shot with perfect knowledge of the base rate of interactions, one-shot interactions in the population. What happened is that selection favored designs with a very high probability of cooperating given the rational belief that the interaction is one shot. Probability is 70 to 90%. Even with modest gains in trade and a modest number of encounters for those interactions that were repeated, like 5, which for hunter-gatherers, that's pretty trivial. And that was true even when the base rate of one-shot encounters, one-shot interactions in the population was unrealistically high. 50 to 70% of the encounters are one-shot interactions. So willingness to cooperate given a rational belief the interaction is one shot, that second set of simulations is very apt because most subjects who cooperate in experimental economic games say that they believe the experimenter's claim that their interaction would be one shot. Remember, the experimenter's claim is just another cue from the environment. No group selection was needed to favor this disposition to start cooperating, even given your rational belief it's one shot. And the disposition to cooperate in one-shot interactions was not a mistake. It was not an irrational bias. It's the most adaptive, fitness-promoting decision you could make. So applying the adaptationist program, I hope these examples illustrate that it can reveal sophisticated computational systems that no one looked for or even imagined existed. And it provides a meta-normative theory of rationality. Thanks.
Thank you. Sorry for rushing you.
That's okay.
Great talk. And I think fans in the room appreciate that you referenced the Swiss Army knife in passing. That was real fan service. Any questions? Right.
Hello, thank you very much. I have a couple of questions. Actually, one may be a little bit boring. So my question is, what is the computational difference between what is defined the reference point in traditional prospect theory and the needs? Because it seems to be that I see the language is different, but the way I understand your model is just a way of specifying or defining a reference point that therefore change the preferences in a way that is consistent with the bulk of results of prospect theory. And my second question is, what do we do now? So, okay, maybe we have a perfect cognition for our ancestral times, but now the world has changed. And do you think we make mistake or are just laboratory artifact, which do not care about the biases that are identified on behavioral economics? So this is more broad question with an open answer. Thank you.
First question first about prospect theory. Yes, they did assume that your current, you could think of the reference point as your current state, right? Because gains, the very concept of gains and losses is relative to a current state. In true microeconomic models, there is no thing as a gain versus a loss. It's just changes in utility. And so you could think of it that way, but there's two things. One is they didn't then go show, oh, look, people are irrational. They don't reverse preferences when you specify different need levels, right? They're just, the reference point is just, in the absence of any other information, maybe I don't want to be worse off than I am now, right? But that is a need level that you might have by default. But they never went and specified these different need levels and then said, look, there's no framing effects when we're specific about that. They did realize that that something about the pragmatics of the situation changed people's behavior, but what Mishra and Fiddick were showing is that it changed it by changing the need level. So there's that. Secondly, the explanation they gave was in terms of preferences. The shape of utility curves, et cetera. It was the shape of the curves. It wasn't like the optimal foraging model. So that's a different theory of why you do the thing. The second thing is, what do you do about the fact that we live in a modern world? I think this is what you're asking. What do we do about the fact that we live in a modern world? It's really different. Perhaps we would like people to make medical decisions. We'd like our doctors to tell us correct information about what a treatment will do, et cetera. If we understand how the mind represents things like probabilities as frequencies, then you can actually have patients make informed decisions. And Geert Gigerenzer is on a campaign to do this. He's been educating physicians. He's been using icon arrays like I showed you for the kids. If you can flip in one training session doctors into doing things and answering those kinds of questions about medical risk correctly in one session. More importantly, by doing these icon arrays like what I showed you, but with people who have been, for example, screened for prostate cancer versus who have not been screened for prostate cancer, and then you see how many people got the disease, and et cetera. You can show at a glance to anybody. You can see how many people had side effects as a function of the treatment, and so forth. And my own view, and I had to make a lot of complicated medical decisions this last 6 months. I Gigerenzered it. I made everybody give me information as frequencies, not as relative rate risk. So, for example, they'll tell you if you have, after mild forms of breast cancer, if you have radiation, it'll cut your risk of recurrence of breast cancer in half. Woohoo! Well, that matters whether that's from 2 in 10,000 to 1 in 10,000 or 20% to 10%. These are different, they mean different things. But when they tell you the possible negative side effects of a treatment, they always give that as absolute frequencies. Don't worry, general anesthesia only kills 1 in 10,000 people, right? It needs to be, I think it's medical malpractice to not be communicating information to patients in these natural frequencies and preferably with the icon arrays. That's one thing. You had part of your question was about the behavioral economics thing too. And I don't remember that part. I think we're kind of lucky that we evolved under these small scale ancestral conditions, because it actually makes us a lot nicer than we would otherwise be in the modern world.
Hi. So I also have a couple of questions. So yeah, I guess the view that you presented is an attempt to explain why apparent biases and errors in let's say cognition they are not so as long as you shift to the goal of what needs to be explained. That's more or less. Did I characterize correctly? Okay, so I wonder what do you think are the roles of things like exaptations or even cumulative experience in explaining some of the things that seem like errors or biases and so on. For example, in exaptations, I can think that if you have a certain tool like an axe that you cut trees with it, you figure out you can use this tool to engage to the war or to prepare food and so on and so on. So the axe is not perfectly adapted for war, but if you have an axe, it's better than if you have a sword because you can use the axe for more things, plus your fitness will increase. So then if you try to analyze if the axe is good for war or not, you say, no, it's actually, there's so many problems with the axe used for war, but actually, so it would be an example of exaptation that explains the current biases. That is not a problem for evolution. It's just, and the other topic is the cumulative experience. I like
well,
to.
Can I
yeah,
answer
sure,
the first thing first,
sure.
because I'll forget everything you just.
Sure. Go ahead. Yeah.
First, I would say that in natural selection, everything's an exaptation because everything evolves out of something else.
Perfect.
And so there's no non-exaptations, right? Everything evolves out of something else. That's for sure true. I'm interested in organic evolution.
Right.
I'm interested in the study of adaptations produced by natural selection.
Right.
In the Darwinian sense.
Right.
And in that sense, an axe per se would not be an adaptation. There are adaptations that allow us to produce axes, things like axes. So we have an object mechanics for how objects interact in the world. We have concepts of goals and the idea that a person can have the goal of solving a problem, and so they design a tool for that problem, and by 7 children have the idea that the function of a tool is what the person who created it designed it for. Those are, well, there's a debate about whether the 7-year-olds, that inference is an adaptation, because younger children think it's it's designed for anything a current user uses. Those are the adaptation, having opposable thumbs that allow us to manipulate. Those are all adaptations, and the ability to make tools in general is probably a selection pressure for some parts of that, but not an axe per se in our sense would not itself be an adaptation. But any adaptation that exists, it can be deployed for different purposes. So in Ugo and Dan's book, in The Enigma of Reason, they give a beautiful example of writing systems which end up colonizing the shapes of letters, colonizes a particular part of your brain near the fusiform face area. And they talk about how in cultural evolution, in what kinds of simple systems are going to become widespread and so forth, it may matter that you have adaptations like, the face area has to do configurations regardless. Every face is basically the same. You're just looking at tiny differences in the configurations, and so it kind of makes sense that this would be used for writing, and so on. So I'll be talking on Friday about how theories from evolutionary psychology can inform theories of cultural evolution and so forth. But basically, yeah, I don't think of, I just wanted to clarify, some people, like Boyd and Richardson, would think of an axe as an adaptation under certain conditions, and that's not the kind of thing I'm talking about. So
right. No, sorry. I give the axe as a kind of metaphor for kind of real biological adaptations, like the number of cervical vertebrae. In mammals is always 7 more or less. So you have constraints.
Oh yeah, there are tons of developmental.
Right.
I mean, this is a fin too. I mean, in a whale, right? There's tons. I mean, everything is built that way. So that's one of the ways that we trace phylogenies too, right?
So
Well, not anymore, but anyway.
So
yes.
is there the possibility that some things are not perfectly adapted for
I don't know
function?
what perfect would be.
Right, exactly, that's it. Okay.
There's no perfect. All optimization happens under constraints. This was actually John Maynard Smith would talk about that. He was designing airplanes during World War II.
Yeah.
He was saying, what would an optimal airplane be? You got to tell me what's the, what I have to make it out of, what's the price of these things, all kinds of different things. There's no out of context concept of optimality. Natural selection designs things that are insanely good at doing problems that were recurrent and had large fitness consequences over many generations. But I don't think that there's such a thing as optimality and independent of constraints.
Can I still ask the question? Yeah, the second one about experience. I like the example about colors. The colors, and I wonder what your opinion is about the dress that broke the internet. That half of the people they saw it as blue and white. And so because this was a bit studied, and it turned out that the amount of exposure to blue light determined whether the individuals saw it.
So if you're exposed to blue lights, do you see it as the gold blue, or do you see it as I forget?
I always confuse as well. So but experience was fundamental to determine. So this is more like a cumulative experience that determines your visual.
Yes. You have lots of mechanisms that get calibrated by your everyday. They're designed to be calibrated by your everyday experience. Nearsightedness is like this too. If you're hunter-gatherers aren't nearsighted in general. Their average focal distance is something like 15 feet. It's like 5 meters or a little less than 5 meters. And the lens, the shape of your lens gets calibrated by your experience. And, so imagine you take identical twins, raise one among the sun in Botswana as hunter-gatherers, and the other one you raise in California, where they're staring at their iPhone screen and the TV and reading books up close. Your average focal distance is going to be shorter, and your lens is designed to calibrate to that average focal distance. And, people like me end up incredibly nearsighted. Although not now, because I'm transhuman, right? I have artificial lenses inside implanted in my eyes. So lots of our mechanisms are designed to calibrate to conditions. And so with that dress, which I only see as the blue gold, I'm interested that they've now figured it out. It's not ridiculous, the idea that you calibrate to your system would be designed to calibrate to average conditions. I mean, in some sense, that's what's happening with the red, with sunset, right? You're subtracting out the red light, so maybe what's happening is you're subtracting out blue light when you're under blue lights too much. I would never want to speak for something that technical in visual perception.
Thank you. The audience that follows us on YouTube left a series of questions. I'm only picking one. Ellie Danziger asks, can every module in the mind be considered as subject to adaptation? In other words, is the whole human mind a unit of selection?
Is the whole human mind as a unit of selection? Well, first of all, let me answer the first part of that question first. It depends on what you mean by a module. If you mean something that's well designed for solving a particular task, I think that in the Enigma of Reason that Hugo Mercier and Dan Sperber have discussed this really nicely when they talk about some modules that are evolved by natural selection and others that are acquired, like the recognizing the letters. I thought that was a beautiful example. So there can be computational specializations that are not themselves adaptations, but that use adaptations, that adaptations are used to create them. Because just because something's a computational specialization doesn't mean it's necessarily was directly selected for. An interesting case, if I could just, for 1 second, an interesting case that Brad Duchesne, who's at Dartmouth, looked at has to do with face recognition. Because he was saying, look, you can have a computational specialization for recognizing faces, but was that produced by something that evolved for faces? And so he started to study people with developmental prosopagnosia, basically back when nobody was studying them, because these are people that never acquired the ability to recognize faces. And he was able to show that they are able to acquire expertise at recognizing many things where the configurations are very similar with slight differences, like men's dress shoes, which are hard for me to tell apart. All kinds of domains, greebles, if you know what the greebles, they were able to acquire expertise for all kinds of things that were not faces, which argues that it's not, the face specialization is not merely because we see lots of faces or a domain general expertise acquisition device, but there seems to be special about the faces. And he did I really recommend, if you get a chance, to look up Brad Duchesne's work. It's very elegant and cool. The second thing, so is the whole mind, I don't think anything, let me just say no. You have a lot of different adaptive problems in life. Foraging is one thing, picking a mate is another thing. There's going to be different selection pressures for them. But the thing that's hard to think about natural selection, evolution, natural selection, is it's happening over deep time. And so, mechanisms are selected for not based on the average consequences that they have over thousands and thousands of years. And I think that ends up, otherwise, do we have one physiological mechanism? No. And I think it's the same for the mind.
Thank you for the very interesting perspective. So I think it was crystal clear from what you showed, from the example you discussed, how any explanation of the computational systems we have should take into account the original ecological conditions. I just wanted to check with you to what extent you endorse a claim that you made somewhere in the beginning, that experiments should all be ecologically valid. Because it seems to me that, especially in light of what you said, there is still some value for non-ecological tasks. Okay.
Oh, no, I don't want to say that all experiments should use ecologically valid stimuli. In the study of vision, perceptual illusions, they do illuminate the way that vision works. And in fact, originally, Kahneman and Tversky made an analogy between what they called cognitive illusions and perceptual illusions. And the idea was to see, the idea was, well, they don't talk about evolution and design, but the idea was you can get at how our mechanisms are designed by identifying these illusions. My point is a different one. My point is that by never studying, well, actually they did have results with frequencies, and it's more like a footnote in their conjunction fallacy paper that they don't get the conjunction fallacy when they redescribe the Linda as a bank teller and feminist problem as imagine 100 people like Linda, then the fallacy goes away. But in general, they didn't ask themselves what would be the kind of data that the mind was designed to use to answer probabilities. So no, it can be useful to study color vision under sodium vapor lights, for sure, right? And it's good that under incandescent lights, I presume that Thomas Edison and the others wouldn't have made a fortune if they were producing incandescent lights where everything looked wrong under them, right? So I am not advocating that you never study anything under ecologically invalid circumstances. I'm advocating that you do also study them under ecologically valid circumstances, and especially that you do that before you conclude that there's no sophisticated machinery for solving a particular problem.
Thank you very much.
We done?
And see you all on Wednesday at 2 for the third Jean Nicod lecture.
Okay, thank you.